In this video, I want to talk a little bit about a limit here. And that limit is this guy. The limit as theta goes to 0 of sine theta over theta. You might see it with x's instead, sine x over x as x approaches 0. Same thing, I used theta just to remind us that we're thinking of an angle here. And we'll show this via the squeeze theorem. And the whole idea here is we're going to make three areas in some sense. The first area is going to be the area of this triangle, kind of with the red line. The second area is going to be the area of this sector of the circle. And the third area is going to be the area of this larger triangle in blue. So let's say this is a unit circle, so we know that the radius of the circle is 1. So we'll just put a 1 there in black to say that. Well, we know this coordinate here for a unit circle. This coordinate here is, of course, cos theta, sine theta. Remember that on a unit circle, that's what cos and sine are, the x and y coordinates of the point on the unit circle where that ray at angle theta intersects. So that's great. So we know that the height here is going to be sine of theta. Fantastic. So we know that length. Now let's quickly figure out the blue length. There's two ways to do it. They're essentially the same way. I'll just tell you both really quickly and we'll just write down one. So the first way is realizing, well, what's tan theta? So remember, tan theta is opposite over adjacent. So it's going to be this side over 1. And all we're left with, since we're divided by 1, is this side. So this side is tan theta. Or we could use similar triangles. We know that this triangle with the red side and this triangle with the blue side are similar. So the ratios of the corresponding sides must equal. So we could say, let's call this side here x as our unknown. So the red triangle is going to be, let's do sine of theta over cosine theta. So that is the height and the base. And that must equal our unknown side x over 1. So again, the height and the base, we can do that since they're similar triangles. And then, well, what does that mean? That means that x is sine theta over cosine theta, which is, of course, tangent theta. So we have a length for the blue side now. And I want to point something out. So we are indeed taking a limit as theta approaches 0. And remember, that means that we must approach 0 both from the right, but also from the left. So as we're approaching from the left, kind of our signs are going to change to negatives. So that means, well, we can just take the absolute value, and that covers all of our cases. So let's say, so we're going to think of this as the absolute value of sine of theta and the absolute value of tan of theta. That just covers kind of the mirror image case if our theta was negative here. All right, great. So our setup is almost complete. Let's figure out the areas that we're going to compare now. And the whole idea is we're going to let theta approach 0. So we want three areas that kind of differ away from 0, but as theta gets smaller and smaller, those three areas start to get closer and closer to each other. So let me kind of just draw another line in here. So if we make the angle smaller, so you can kind of see what's going on. So the three areas are going to be this red triangle, this sector of the circle, and this blue triangle. And you can imagine with a smaller theta, the difference between those areas would be very small. Think about what this diagram would look like with this smaller theta, and you can see that the difference between the areas of each of the three figures we're looking at would be very, very small. So that's kind of the idea here. Okay, so let's go to it. Let's calculate the area of this red triangle. Well, that's easy. That's a right-angled triangle. It has height sine theta and base cosine theta. Remember, this length here is cosine theta. It's the adjacent side of the triangle here, or it's the x-coordinate of the point where the ray meets the circle. So we know that this red area here, maybe I'll actually color it in red. That area is going to be base times height divided by 2. So sine theta times cosine theta divided by 2. Now, we know that that's included in this sector of the circle. So we know for sure that this is going to be less than or equal to the sector which I'll color in green here. So here's our sector in green. It captures all of that red triangle. So what's that area? Well, the entire circle has area pi r squared, and r is 1, so the area of the circle is pi square units. And we're taking theta over 2 pi-ths of that circle. So 2 pi would be the entire circle. So we want theta, I'll do this in green to match up. So we want theta over 2 pi-ths. So that's the ratio of the circle that we're taking. And the area of the circle is pi. So these pi's, of course, cancel, and we're left with theta over 2. Okay. And then the blue triangle, again, I'll color that. That subsumes all of the green sector of our circle. And we know the area of that's just going to be base times height divided by 2. So tan theta, let me put less than or equals to in here, less than or equals to tan theta times the base, which is 1 over 2. And let me put my absolute values in there. I forgot that. They won't be that important a little bit later, but just because we do want to deal with both sides of 0, we want to have our absolute values in here. Fantastic. Okay, let's clean this up. I'm going to multiply everything by 2 and just write things down here. So we have sine theta times cosine theta is less than or equal to theta, and let me put my absolute values in here, is less than or equal to tan theta. Great. Now, remember, we want the limit of sine theta over theta. So here we have a theta, kind of, you can think of this in the numerator, so this is like theta over 1. Let's take the reciprocal of everything, so it ends up in the denominator. So we're going to have 1 over sine of theta cosine of theta. Now the inequality switches since we're taking the reciprocal. 1 over theta is greater than or equal to 1 over tangent of theta. Great. Okay, so we're almost there. Let's multiply everything by sine of theta, the absolute value of sine of theta. So let's go ahead and do that. I'm going to multiply everything by the absolute value of sine of theta. So our first term, our second term, and our third term in our inequality. So let's make some more room. We'll go over here. So you can see that we have an absolute value of sine theta, which is going to cancel out with this absolute value of sine theta. So we're going to be left with 1 over the absolute value of cosine of theta is greater than or equal to the absolute value of sine theta over the absolute value of theta, which is greater than or equal to, and then we're thinking about this as now this is sine over cos, and 1 over sine over cos is cos over sine. If I multiply everything by sine, I'm just left with cosine in the numerator. So you can check that if you like. Now what's cool here is we can drop the absolute values. Cosine is definitely always positive around 0. Cosine of 0 is 1, and cosine of stuff around 0 is still positive, but just less than 1. So we know it's always going to be positive in the range we're looking for. So I can just mark out those absolute values. We don't need them. Same with the ones on the right-hand side here. Okay. And now let's look at the middle of this inequality. Well, when theta is negative, sine is negative, so this entire thing would be positive. And if theta was positive, sine is positive, so everything would be positive. So no matter what the sign of theta is, sine theta over theta is going to end up being positive. So let's get rid of those absolute values too, because they're unnecessary. Fantastic. And now it looks like we have something where we can use the squeeze theorem. We have our squeezing functions, 1 over cosine theta and cosine theta, squeezing the thing we're interested in, sine of theta over theta. So we'll go on to the next board here. And this is what we have. So we can take the limit of these guys, thinking of what the limit of cosine theta is as theta approaches 0. Well, that approaches 1. So this limit will be 1, and same with the right-hand side. So let's go ahead and do that. Let's take the limit as theta approaches 0 of 1 over cosine theta. This is a nice function. There's no weirdness going on, so we can just plug in 0. So this is going to be 1 over cosine of 0, which is, of course, 1 over 1, which is 1. And, let me color that. That is, let's say, this blue part of our inequality. Now let's do the limit as theta approaches 0 of cosine theta. And similarly, we can just say that's 1. You plug in 0, you get cos of 0 is 1. And that'll be this red bit of our inequality. So the limits of our squeezing functions is the same, so that means that the function it's squeezing must have the same limit as well. So we can say, by the squeeze theorem, we have that the limit as theta approaches 0 of sine of theta over theta equals 1. Great. I do want to talk about what this means. So we're taking a ratio of two functions, sine theta and theta, and we're getting the number 1 out of it. So what does that kind of mean? Well, what does it mean when you divide two things and you get 1? It means that the two things you're dividing must be the same. So what this is saying is that near 0, sine theta and theta, the functions f of x equals sine x and the function f of x equals x, behave the same way. So you can kind of see that in the graph of sine theta. So if I graphed sine theta, I'm just going to sketch it. I think you guys remember sine theta looks roughly like that. And if we zoom in on the origin when x equals 0, so we'll zoom in here. And we get something that looks like that. So around 0, you can see that these functions look the same. What does the line y equals x look like? Well, that looks like a straight line at 45 degrees going through the origin. So as you get closer and closer to 0, sine of x starts to look a lot like x. And that's what this limit is telling you. As an exercise for you guys, we can show that the limit as x approaches 0 of 1 minus cos x over x equals 0. And to do this, you're going to have to remember that 1 minus cos squared x is the same thing as sine squared x. You can kind of just rearrange sine squared plus cos squared equals 1 to see that. And the other thing is remember that the limit as x approaches 0 of sine x over x equals 1. So those two facts will help you with this exercise. So try that on your own and see how that goes.